Just need him and tell him when to start and all. Okay.
ठीक है. हाँ लगी क्या ओ बीच में आना जाना नहीं
देख के आए
Hello, check. Hello, hello, hello. Check, check. Hello, hello. Hello. मीरा जी किससे मांग के आए राजन से मैं अपना भी दे देती हूँ बेटा लगा बट मैं वो टेस्ट करना चाहती हूँ मैंने नया लिया ही दो के लिए
honestly, as I told you,
तुम लोगों को बात ही नहीं समझा रही है, तो क्या करेंगे ना फिर हम ऐसे जाकर कई कई लोगों से कम्युनिकेट करोगे तो तुम लोग एक इलाका
बजट किससे करना है? बजट तो इसमें भी आया है। You can check on the website on
Website one.
हाँ I think sit somewhere there.
Yeah. This will be enough.
No, this is not professional.
Okay.
What is it? थोड़ा फनी है बट इससे बेटर नहीं मिलेगा।
But just say the website.
What is the website? अरे इतना what is the website?
Just say the website.
myinstance.com.
Okay, my instance.
See after 10 we करें after 12
After. After 15.
just sit.
There.
It's started.
Good afternoon, everyone. We will be starting our event right now. So, I welcome you all to the annual Meera Memorial Paper Reading Competition. The annual Meera Memorial Paper Reading Competition is a prestigious event where students, undergraduate students and postgraduate students get the opportunity to present the paper in front of an audience. This is a great opportunity for everyone to learn and adapt in future also. The top 3 presentation will be rewarded, and first years are specially encouraged to participate. There will be a recognition prize for the best performance done by first year. So, yeah, I'll be introducing you to our judges. We have had the privilege of having our respected professor, Dr. Gitanjali Sethi and Dr. Annu Malhotra as our judges, and Mr. Lavnish Kumar as the student judge. I'll be heading towards the rules. Please listen carefully. Each participant will be given 15 minutes. The timer would start the moment the participant starts screen sharing. 12 minutes are given for the presentation and 3 minutes are given for question and answer. Buzzer will be pressed once at 10-minute mark and twice at 12-minute mark to indicate the completion of presentation time. Marks will be deducted if the presentation exceeds 12 minutes. Are the rules clear? Have anyone any questions? Okay. The decision of the judge would be final. We request the patience of participants to wait for the results. Also, the session is being recorded. If anyone has any objection with the presentation being recorded, please kindly inform us in advance. I request everyone to keep their phones in silent and not to walk out of the room during a presentation. With that being said, we will start the annual Meera Memorial Paper Presentation Competition. So our first participant is Ishan Prasad from Ashoka University.
I just have a question.
Yes.
What are you expecting for questions? The judges have to ask or it's open to house?
No, judges have to ask.
Only the judges. And nobody from
If time is left, 3 minutes I thought question and answer.
that 3 minutes includes 2 of us, or 3 of us, and
If time is left.
if time is left. But if it's an open house question, does it get included in the marking?
Yes, you can. It's up to your discretion.
After Ishan Prasad, I request Anushri Srivastava from St. Stephen's College to be ready.
So this will not, is it okay for you? Is it okay for you?
Can we leave the time? I can't see it.
It's up to them.
My display is not actually to see. Hello everyone, today I will be presenting on characterization reversal of magnetic nanoparticles for biomedical applications. We'll be discussing the synthesis, functionalization and the simulation of these particles. So a bit of context, I am a third year at Ashoka University and I am part of the complex magnetization characterization laboratory at Ashoka. This is under Dr. Sushmita Saha and I am working with the PhD student Krishna and the funding for the lab is provided by Ashoka. So we'll move on to this from what we are actually doing. So the motivation for our work is something called hyperthermia. First of all, let's clear what nanoparticles are. They're nanoscale objects, which and for us, we'll be working on magnetic nanoparticles, and these are of the order of 1 nanometer to about a micron, like 1 order less than a micron, and they are used for a lot of applications. And the application we're interested in is called hyperthermia. So hyperthermia effectively just exploits the hysteresis loop of a magnet in order to cause local heating, and this can be used to destroy cancer cells. So here we'll be using alternating magnetic fields in order to basically destroy cancer cells within the body. So this is our far off goal and we're slowly going towards reaching our goal. But this presentation, I won't be focused too much on hyperthermia, I'll be focusing on the process of actually reaching that. So for starting off our work, the synthesis includes a chemical reduction reaction, wherein we're using nickel chloride hexahydrate, hydrogen hydrate, ethylene glycol, sodium chloride, with this chemical reaction that takes place. One thing to note is that when we're actually synthesizing these particles, we have to ensure that they're heated for a particular amount of time. And there are a lot of precautions that come into the way of doing the synthesis, and for more information you can look at the reference. So we basically synthesize particles of different concentrations, like molar concentrations, which are listed here. And the reason for this was because the paper that we were following also had a variety of concentrations. We wanted to look at how concentration will play into those further. So after synthesizing the particles, which look something like this, so this is because the magnetic, they're obviously agglomerating as well, right? So that's why we see them as macroscopic objects. But then when we did some characterization, so first was FESM, which we did at the central facility at Beirut. So these are FESM images. From here, we use image A in order to calculate the particle size. And this is the FESM images for the 45 millimolar sample. So with this, what we do is we use this scale in order to calibrate, and then from here we can measure these individual blocks that are nanoparticles, and this gives us an average particle size of 150 nanometers with this standard deviation. This is quite higher than what we were expecting based on the literature, but reasons could this just be the agglomeration of these particles, and further work is being done by using like stabilizing agents and other chemicals in order to have them less agglomerated together. Next, we also did some XRD, which gave us these peaks, which which obey what literature also tells us, and this is an FCC lattice. Here we know that the crystalline size is actually 15 nanometers, and this is actually something that we have to understand properly. And from very preliminary understanding, it could just be that the magnetic particles are agglomerating, which causes a difference in the sizes between the FESM images and the XRD data. So to work around this, we are also scheduled for a TEM slot, which will help us zoom further in, where we will be able to tell the particles apart. Next, we did VSM, and VSM is basically the introduction towards going towards the magnetic properties of the system, and VSM being vibrating sample magnetometry. This gives us various values like universal field, saturation magnetization, and the saturation field, and we get a hysteresis loop which looks something like this. Obviously, this is ferromagnetic, and one thing to note is that if we had reached a particle size of about 20 nanometers, we would be in the super paramagnetic region, which would mean that these particles are effectively ferromagnets, but they also show properties like paramagnets as well, which is used in a lot of other places. For example, a lot of work that is being done on, say, nanowatts, magnetic nanowatts, are in the paramagnetic region. So that is just a side. What happens when we are using VSM is that the particles need to, because we have a powder, correct? Using that powder, we need to basically roll it into a ball, which would have spherical symmetry. Now, this spherical symmetry would mean that there is no in-plane and out-of-plane measurement that we have to take separately, and there is only one hysteresis loop that we are taking. So from this hysteresis loop, what we want to do is, because we do not have a lot of facilities like FESM, XRD at in-house. So what we try to do is we move on to simulating these particles in order to get a general idea of the hysteresis, so we can work on optimizing our synthesis process further. And from here we move into simulating these nanopparticles. So we do our simulations using this software called Minimax 3, which solves the LSG equation, which is given here, and these are the parameters that we are using. And all of this comes from this paper by Anjan Varman, and so it is a paper by Anjan Varman. I am forgetting the name of the time. I think it was Dr. Viwas from Excellos. So these are the parameters that they also ran, but they ran it in a different software. So we're just trying to replicate ourselves. The diameter is 50 in order to just compare with the results that they have. And then from here we'll be taking these things further in order to actually get closer to what to the data that we had experimentally. So first we start with what these simulations are entailing. So suppose we have a single spherical particle. What this does is that here we see that there are only two states in the magnetization process. Here we're simulating a hysteresis. So we're going from -1 to +1 Tesla, which gives us the magnetization values. Now, because of the spherical symmetry, these are actually 3D spheres, and the ring is just these units from it. So we basically vary the field from -1 to 1 Tesla, and what we see here is that there are just two states that we get. So here, this is in the negative y direction, this spins are in the negative y direction, and here it's in the plus y direction. There is a binary of states, and there are no actual changes in the middle here. Right? There is a spontaneous flipping because of symmetry, and this result is consistent in the x and the y direction as well, just because of symmetry. So what we see next is, we saw how one particle is working, right? Then we move on to a chain of particles. So for that, we simulate these chains. Now, here, because the shape is different in the x and the y direction, we expect different behavior of the magnetic field and the hysteresis. So here, this is very similar to the hysteresis that we had obtained earlier, right? And the reason for that is because the shape is in the x direction. So the shape and isotopic energy actually assists the magnetic field, which is applied in the x direction, to orient the system into just the two states again. So there is a left aligned state and a right aligned state, which you can see with the spins here. There is no intermediate state which is somewhere in the middle. Then, when we have this idea here, this is the field along the x direction. Then we see what happens when the field is oriented along the y direction. So, when we have the rectangular chain, when applying the field along the y direction, this loop is very, very thin. And one interesting thing to note here is that there are intermediate chains. And these intermediate states are because of the competition between the shape and isotropy, which is the energy which is effectively needed to flip the spins completely from an up to a down state. If you stand, suppose on the chain, and if you look up, that is very different from, as in the y-axis has no symmetry like the x-axis did. So that's why we see these different results. And the competition between the shape and isotropy and the external magnetic field causes the system to gradually shift. There is no immediate shift that we saw earlier, and there are these states, and that's why the hysteresis loop is like this. And this is a magnetization reversal in our chain. When we have these basics clear, what we figure out from here is that we need something of this shape and something of this shape. So in order to mimic our ASM data, we move on to something which looks like these nanoparticle beams. So here, the hysteresis loop is very much like what we had obtained earlier, and this is a magnetization reversal that we see, which goes from minus 2.5 to 2 Tesla, and you can see the reversal happening in this. So we note here that this and these, so the spins, the particles with spins oriented along the x-axis do not show that intermediate transition, right? Your x spins orient from a left to a right immediately, while these chains, which are not aligned to the direction of the x-axis, these have an intermediate shape, and this hysteresis loop also gives us how the spin is actually changing. So when this is our last point, this is the point where not all of them are completely oriented along the negative, oriented along the positive x-axis, because the journey traces this direction. Here we see a jump from this place to this place immediately, right? Then we make this shape even more interesting by adding a nanoparticle in the middle. And what this does is greatly reduces the width of the curve. And something very interesting to notice here, the spins just split in the center. And this is happening because this spin, the one in the middle, is getting completely balanced. And okay, I can point this out further. We can see this here. So for 0 Tesla, the spins are still flipping, and the middle spin is still towards the negative x direction. But at 0.01 Tesla, the spin has flipped, but the others have not flipped. And this is like a very interesting result. This spontaneous flipping that is happening at a magnetic field which is much lower than what causes all the spins to orient is something that we obtained from this study. And to explore this further, I also moved on to 2 chains. So instead of just one chain, there was another chain like this, and this shows another very interesting process in magnetization reversal. We see when these spins are like the inside is very similar to what happened earlier, but when we see here, the spins are in the opposite direction to the other chain, which is very, very similar to what we see when we have something which opposes the direction of the chain, which opposes the change in the magnetic field. So this is just what we obtained through this. This is more of a tangent to the hypothermal measurements, of course, because this was just some interesting results in the magnetization and reversal that we obtained while simulating. That's why I wanted to share these results. Further, this is just, that was all, and this is our future work. We'll obviously be delving more into the hypothermal measurements in order to measure the heat loss. We are also looking for the time slot like I mentioned earlier, and we'll be dealing with the problem of size control and the minimization of accumulation. Also, the simulations were at a cell size of 5 nanometers, which means that the lowest time is 5 nanometers, and then we'll be working further on core cell structures. So, thank you.
Can you go back to your initial, I think second, where you had given estimates of diameter, what you So you are saying that you are getting something around 150 plus minus 30. What do you expect otherwise?
We were expecting something in the range of 60 for the 45 minutes.
Because what you are simulating is for 50,
Right.
right? And what you are getting is 150, which is
Way less.
I mean, if I look at the analysis that you've done using multiple elements in the chain, right? It's equivalent to almost having 3 elements in your system. I mean, in the sense, 3 spheres, right? And the behavior changes if you have 1 or 2, and there is a third one in between, right? So, don't you think that simulating with 50 and trying to simulate using 50 and having something like 150 can actually be a very drastic?
Definitely, I completely agree that the simulation is not at all a representative of this. So this was just the process of going through simulations, and the problem with Vmax is that it takes a lot of time to print out results, and the 50 is just our initial step in going towards the 150. Because I also mentioned of the difference between the FESM and XRD images, right? The 50 provided a good ground to start literature review from based on the normal paper. That is why we got to 50. Plus also, if we have further analysis, we can definitely run these simulations again. So the 50, I agree, is not at all a representative of the 150.
So since you are doing simulation, what stops you from going from 50 to 150 to begin with? Just because you were trying to replicate results?
No, so 150 to 50, the reason for that is because of this discrepancy between the KSM and the XRD. So, yeah, so because we don't have an exact value of what the actual size is, we're confused with, because it doesn't make sense to have a lot of 150 data when your nanoparticle is nowhere close to 150. 150 could also just be human error measuring, because we're not sure if these are actually abnormal.
So why do you say human error?
Because the imaging calibrations are the ones that we do. We are manually measuring the diameter of these
So
particles.
can you just tell me quickly what you mean by manually measuring?
So with image, we have to measure the data, as in like with the calibration. We use that calibration data to measure the particles actually. The statistical analysis of those particles. It's just calibration we do by hand.
Cursor at the ends. You put the cursors at
Yeah.
the 2 ends and measure.
That is how we're measuring the size of the particles.
How is the size of these nanofactors related to their magnetic properties?
So, like I said, when you reach a particular level, 20 nanometer generally is the cutoff point where we get to super paramagnetic behavior. Wherein super paramagnetic would basically mean that if there is no external field of light, they are not magnetic in any way. So if we reach that size, that is quite good for biomedical applications, because we don't want a ferromagnet inside the human body, because it could lead to other complications. There is a lot of literature on that as well. So 20 nanometers would be the best size that we can go for. But if we somehow manage to have a very immediate injection and removal post process, then ferromagnetic is not a problem. But 20 nanometer would be the perfect one where we can easily take it out of the world.
Even if it's there for some time.
Super paramagnetic would be the region that we want to activate.
Are there any more limitations of using them for medical purposes?
So, ferromagnets, the problem with biomedical applications comes into the field that you can actually subject to the user. So you can't have a very large velocity stresses, because that can definitely lead to other complications. Plus, there are like regions of magnetic fields which you can subject to the human body, and if you don't get a big stresses to that region, then there's no actual advantage of using it, right? So we want to minimize any complications that we have.
tell me how are you generating fields of one test?
So that was a simulation.
No, like if you're doing an experiment, if you are going to generate a field of one test, how are you going to do it?
Oh, so I think in real cases.
Yes.
So this was using the ASM. This is inside the ASM.
Like what kind of principles do you use? Because one test line will use very strong magnet, correct? So how are you generating those kinds of fields?
So this is all that happened inside the ASM.
This there should be
What is
some.
the principle behind, mechanism behind, how does it generate? ESM has some.
Right. So I'm actually not sure for whether the generation actually happens, but I would guess that definitely using like electromagnetic actually generate such a.
And one thing also is when you're dealing with the properties of metal particles, what kind of ideas are you using? I mean, all the statistical properties you're dealing with, what kind of theories or models are you working with? I mean, today's when you're showing how the spins are dealing with as magnetic fields, what kind of mechanisms are you using?
So this is solving the energy equation.
And where does this equation come from?
This equation is the standard equation for energy. Measure the change in magnetization with respect to time and how magnetization is affected by. So LSD equation basically talks about how the magnetization precesses around the external effect. So this is the damping term which Wilbur provided, and it's just measuring the magnetic field.
You said nanoparticles, particularly you've been talking about sizes 20 nanometer or 50 nanometer. What happens at these specific points? What changes? How is the change taking place? What is the phenomena or anything?
Generally, at the nanoscale, the whole thing comes down to largely surface to volume ratio as well, surface area to volume ratio. So, if you have, suppose a microscopic object with sides 1 centimeter by 1 centimeter or by 1 centimeter, so the surface area is 1 centimeter square, but the volume is 1 centimeter cube. So that's 1 per centimeter. Correct. So when you go to the nanoscale, this number becomes 1 per nanometer, which is like 10 to the negative 9 goes to the numerator, and your surface area per unit volume is very, very large, and that changes how the properties of the system actually.
Do you think it's only the surface to
That
volume
is
ratio
the-
that is the main important thing, whereas I think the spin is mostly related to how the electrons are placed inside or how we behave within. So, what is more important? Is only the surface to volume ratio important, or is there something other phenomena or some other physical significance that one can talk about?
So as of now, with this process, we're not interested in getting a particular size because
No, because you said that it becomes a supermagnet. So if anything becomes a magnet or a supermagnet, it has to do with its structure. So rather than only surface to volume ratio, you should be talking about structure or something which is going on about electrons and that or something like that.
Thank you, Sean, for the presentation. Now, I would like to invite Anushri Srivastava for a presentation. And after that, I want Ananya Samhita from Ashoka University to be ready with their presentation.
So you will have to tell us, you can't tell me like this that 15 minutes are over, right? So you have to stop us from asking questions if you want us to stick to that. Right? Whatever way you want.
Very good afternoon, everyone. I'm Anush Shrivastava, first second year physics on the Student and Science Studies College. And today I'm going to present on exoplanet detection analysis. So I'll go about this flow. I'll give you a brief introduction about what are exoplanets and why do they matter, and then the various detection techniques which are there. And then I'll pick out 2 techniques out of the 6 techniques and elaborate on that and present results of the computation analysis that I had performed. So coming to what are exoplanets and what is the need to know about them. So exoplanets, per se, the sun is a star and we have Earth. So Earth orbits the sun, so we call Earth a planet. So there are other stars in the galaxy and in the universe. So the planets which orbit those stars, they are known as extrasolar planets or exoplanets. And why do we actually need to know about them? We actually need to know about them because to find life beyond the Earth, to look for a second Earth, to understand about galaxy evolution and to explore intervening environments. The major purpose, like the existence of such celestial objects like exoplanets, reveal a lot of information about how the galaxy has evolved, and also it gives an idea for habitability because there are around 5,500 exoplanets which are known till now, and around 1,400 are found to be known which have the possibility of liquid water which can exist around them. So there is a possibility of life or even possibility of finding energy resources or mineral resources. These are some of the exoplanets examples. For example, this 55 Cantilever is known to have been made of diamonds. That is the example. So coming to exoplanet detection techniques. So there are 6 exoplanet detection techniques which exist in literature, namely transit method, radial velocity, direct imaging, gravitational microlensing, pulsar timing, and astrometry. Out of these, I would cover transit method and radial velocity method in detail. And if I'm left with time, I would like to come back and give you a brief about all the other methods as well. So, but a question of greater importance is what can be actually determined using them. Is it just we can just spot the exoplanet, know its position, or we can know something more from these methods? So we can actually know a lot of things using these methods, such as the orbital period, the time it takes to go around its host star, the distance of the planet from its star, its orbital inclination, information about the size of the planet, and atmospheric composition. As I said, we can look for a potential habitability at and around the planet. So coming to transit method, one of the detection techniques which is there. So what can you think of, what can we observe in the dark universe? We can observe light, and light particularly of the star. So to get information about the exoplanet, we can get information about the star. So in transit method, what we actually do is the blue circle here represents the exoplanet. So when we observe, we put a telescope, we observe the light which we get from the star. And when the exoplanet crosses the star, so the surface area of the star which is exposed to the telescope to get the light gets hampered. So we observe a dip. As you can see here, we see a dimmer light flow. So that is what we observe, and then we create something called a light curve. So the basic fundamental property, just to give you an intuition, is this only. So all the principle behind the transit method can be compressed into 3 major steps. Exoplanet crossing the star. When it crosses the star, we observe a dimmer light. But otherwise, if there is nothing between the telescope and the star, you will observe a constant flux, more or less a constant flux. Then the light curve formation and the repetitive nature. The repetitive nature is important if we see such dips on periodicity. So an essential property of a planet is its periodicity. So if there is a repetitive nature, so there is a possibility that there might be an exoplanet orbiting the star. So what is a light curve? I mentioned light curve. So light curve is basically a graph that represents the change in brightness of the celestial object. So for say, as I said, if the telescope is observing the light, the amount of brightness, the amount of flux that it receives from the star. So when we plot it, so we get something called a light curve. We call this as a light curve. As I said, I want to present the computation work that I have done. So I use a library called a light curve library, which is used to download the data from observatories like NASA and TESS. So, yeah. So this is a data for a star from the Kepler input catalog. So this is something called a target pixel file. This is what you get from the telescope, what you observe. So the region here, yellow, is the maximum flux you see. So there is this thing that there is a star here. So this is what you get, and then you convert it to something called a light wave. So you observe the transit like periodic dips here. So this essentially indicates you or pushes you toward that there might be a possibility of an exoplanet orbiting the star because of these periodic dips. So I would like to present two of the parameters that I have calculated, orbital period and the transit duration. So the black line here represents the baseline flux. Obviously there is some noise, it's not a constant line. This noise can be due to various reasons. There might be due to the motion of the star or some instrumental error or some random celestial object like comets or something crossing in between. But we assume it to be, this is a normalized curve. So we assume a baseline flux as the reference line and then calculate the point where it starts to dip and when it, so this, the distance between these two would be the transit duration. And similarly, if we find out the distance between two consecutive dips, so that will account to be the orbital period of the exoplanet. So this is what I have got, like 3.522 here and transit duration to be 2.73 approximately hours. And this is something which is already there in literature, one of the research papers that I have cited later. So this method behind this is already there and the established values are 2.75 and I was getting around 2.73, which is 30% error, and 3.5 to 19 and I was getting 3.5, which is pretty good. So this is about transit method, but there is one big limitation of transit method that it has a lot to do with the alignment of the telescope. For say if you put a telescope here and have a face on view, then you won't observe any dip here because the light coming from the star would be constant to the telescope. So, but if you put a telescope aligned to this edge on view, then you will observe a dip. So this is a major limitation of transit method, that it has a lot to do with alignment of the telescope. And so there are these blind shots that we take, and if we observe a periodic dip, then it's like we move towards detecting the exoplanet. So to overcome this, I would like to present the next method, which is the radial velocity method. Here the mass of the exoplanet is taken into consideration. So the planets which are heavier, like as comparable to the mass of Jupiter. So we can say like this exoplanet also exerts a gravitational pull on the star. Because this is a heavier mass, so it will execute, and then these two objects will form a system of two bodies, a system of particles, and will orbit around a single center of mass. So again, what we can observe is the spectrum of the star. So here we do not work with the light curve, we work with the spectrum of the star. So if we are able to detect the time period of the star as it goes around its orbit, then that would be equal to this exoplanet as well. So the basic principle is we observe this spectrum. When the star moves towards us, it shifts towards shorter wavelength or the blue shift, and when it moves away from us, it shifts towards longer wavelength or the red shift. So the periodicity in this blue shift and red shift is what we analyze. So some sort of this is a very idealized generated through plate data, but this is easier to explain. So we get something like this, so each time it reaches its peak, it's the nearest point that the star is from the telescope. So the periodic dips here can be computed to get to know about the orbital period and the mass of the star. So this is a real data of a star called 51 Peggy. This is actually the first star which was discovered using the radial velocity method. So these are the data points. So what computation I did, I took this data from Exoplanet Archive of NASA and plotted the radial velocity with these error bars as well. And then the essential part of the computation was fitting this data to a Kepler model. So why Kepler model? Because it's a planet and a star, so we approximate it to fit to the Kepler's law of motion. So we try to fit this data into a Kepler model.
Stop talking.
To a Kepler model whose equation is represented by this. And then we get these parameters. So the K represents the amplitude. Like when we fit the data, to we get something like this. So we fit the data to get amplitude equal to 55.31 and 4.24 to be the orbital period. So this is the orbital period that we get of the star. But because of this method and the center of mass property, so the time the star takes to move around its orbit would be the same as the exoplanet. So this is also the orbital period of the exoplanet as well. And also I had tried to compute the mass of the exoplanet, so which is coming out to be half the Jupiter mass roughly, and that's what I said, because this works more with when the exoplanet is of heavier mass. So this is a comparison between the observed values and the actual values, and the orbital period is like to good approximation, so we can say that the computation works well. Yeah, so the limitations of transit method is overcome here because this has nothing to do with the alignment of the telescope with the star, because you just need the telescope to be fixed, because it requires like the periodicity of the blue shift and red shift when the star comes closer to the telescope and when it goes away from the telescope. So the major differences between the two methods is transit method measures the trimming of the star's life, whereas radial velocity, this can be compared to the Doppler shift that we had studied in our class 2. And yeah, one of the major things is in transit method we can determine the size of the exoplanet, because that's the principle. When the exoplanet covers some surface area of the star, that's where you observe a dip, and that's how it works. So transit method is used to determine the size of the planet, whereas radial velocity you can determine the mass. If you have some clue about what is the information about the star, then we can determine the mass. And also with how do you get to know about the orbital information. So that's the spectrum where it lies. If it lies in infrared regions, that will give us an idea of how the temperature and atmospheric conditions around the planet. These are the future aspects I want to explore in more using direct imaging method, which involves Fourier transforms, and to check for atmospheric conditions.
So, I would like to ask you, by looking at the spectrum from the planet, how can you tell what kind of structure it is made of? Like what particles or what kind of elements it is made of? As you suggested that a planet is made of lag.
Yeah.
But I am only getting spectrum. How are you getting that information from that spectrum?
So this by translating radial velocity method, I have not explored this part, but I have an idea how this works. So this actually works like so you observe a spectra here. So if you get wavelengths in a particular region, so as I said, if the wavelengths lie in infrared region, then we can say that the temperature around it would be an high. That is an approximation that we say that like as we start, so it must be spherical. But then we see how this spectra lies and what is the time period and how does the radial velocity change with time. So all that calculations that give you an idea of like if in the atmosphere there is carbon dioxide present. So when we get the light from the planet, that would be different because of the presence of carbon dioxide. So that change in spectra where this lies and how fast this moves and the amplitude, the K that I have calculated, that was accounts for. But I had not worked on that. That's what we chose.
And one thing is, when you say you're using the redshift of the blue shift, comparatively stars actually light years mostly. Like neutron stars are very thousands of light years away. And the kind of the periodic motion of the radius, the orbital radius is roughly a parsec, so maybe astronomically.
Yeah.
Like in that short distance, how is that? I mean, observations are sensitive enough to measure those kind of things.
The radial velocity method works more with if the exoplanet is of higher mass. If it is of higher mass, then it will have a greater gravitational influence on the star. So the more gravitational influence it will have, so the distance between the center of mass and the star would also increase. So the radius where the star orbits it, that would be bigger, so that would also, that would give a better idea. So this would not overlap. And yes, this is sensitive. We use spectrograms and things like that, and now technology has improved. So this is sensitive enough, so the data is enough.
What is the problem if you use this method for lower mass?
Now, if you use this method for lower mass, then the gravitational influence of this exoplanet on the star would be lesser. So the center of mass would, like if this is very negligible compared to the star, so the center of mass would essentially lie on the star. So you won't be able to recognize the motion of the star along the center of mass. So this blue shift and red shift would not be very visible, not very visible.
And so many other methods that you mentioned, have you worked on all of them, or at least you have an idea about how is, which one is the most superior and for what
Yes,
reason?
ma'am, I have an idea about them, but it's actually very strange that transit method is more of probability and guessing work, because you need to do a lot with telescope alignment. But these graphs shows that the maximum number of exoplanets were detected using transit method. So it is basically that from the transit method we get a rough idea of what would be the orbital period and what could be the thing, and then we verify it using the radial velocity. Because these two are more feasible and more simpler to execute rather than direct imaging or other things. So I have explored these two only, not two.
We go back to your first. Did you actually go to the right way model? Did you read about folding?
Yes, ma'am.
What folding method have you used? You said you read about folding. Type of
Yes.
folding. What folding method did you use? It doesn't matter. It's okay. Did you use box folding?
Yes, ma'am. That was where I used periodograms.
Since you used box folding, did you test your program for multi-planet, more than one planet?
No.
Did you actually do the radial velocity measurement for the same? This is B is what you have studied using radial velocity. Radial velocity.
Yes.
Do you actually look at the right?
Ma'am, I actually tried finding a star which was common for both the catalosphere, which I can get data for both. I couldn't get it for this star. Yeah.
Can you tell me why?
Why I couldn't get it? So that is, I think, one of the possible, I'm not very sure, but one of the possible reasons I can think of is for the mass only. Like if here, as I said, if the planet is of heavier mass, then the motion of the star will also be considered. So if we consider it to be in the transit method, so apart from these dips also we see some more dips which is due to the motion of the star. Because somewhere we assume that the flux from the star is constant. So if the star is in motion, then that would also come. So it would be difficult to detect.
Did you take care of the algorithm while doing the calculation? That's okay. Doesn't matter. So, just to tell you one thing, that you cannot compare the two methods because they supplement each other. In other words, that if you want complete information, then you need both. But the problem is that both the methods cannot be used for the same system most of the time. So it's not like you compare one is better than the other. It's the availability that you can use in case where you can use you can measure the flux depending on whether you do on-site face on measurement or edge-on measurement. Then it depends whether you can actually use it. If you were to actually compare and say which method is the best, that's the direct imaging. Actually, the direct imaging method is, but because the size of the area is so small, when you do direct imaging, it's very difficult to separate out the image. And by the way, everything in cosmology depends on measuring redshift. If you can't measure blue shift and redshift, you cannot do anything. So everything is sensitive enough to making the change. No.
Thank you. you, Anushri, for your presentation. Now I would like to invite Ananya Samhita from Ashoka University to come and present. After that, Odilong Insong, Chris Kerr, and Vibhushi Vare to be ready with the presentation.
Basically there was some discrepancies in the observed power output from the turbines versus what was proposed by the manufacturers who were supplying these turbines, which the company is using. So the problem statement is that when you have a group of 36 turbines, the expected total power output is just basically they were multiplying the power output from one of them into all the turbines, but this is not what is actually observed. And basically my project was to observe these dynamics of the wind farm in order to better predict the power outputs from the turbines. And to do this, I had to determine a coefficient with which I would multiply with the observable speed in order to know the actual wind speed at a particular moment. And also from this, I would get the efficiency that they were and this is the data set I used in a group of 36 turbines located in Gujarat, Kutch. It was owned by Adani Energy, Adani Green Energy. And the data sets were Excel files, very large Excel files, and almost all days of the year, of speed and power output to the turbines at 15-minute intervals throughout the year. And these are the factors affecting efficiency drop, or the wake effect, which is basically that if the turbine is in the wake region of another turbine, then all these factors such as physical arrangement, terrain, surrounding constructions, the rotation of the turbines because of the direction of the wind, and also like turbine inactivity when the turbine go off certain block periods, which would affect this, which would all contribute to the wake. So I had to first do like data cleaning, which is finding zero values, which included zero values from the turbine inactivity, as well as like I had to segregate whether they would come back or whether they would actually go to the speed every time, because up to a certain value the turbines would rotate even if there is wind. And so I had to also make sure that I knew the speed power relationship, because all my analysis was done using speed data. And so if I did this using speed data, I had to know that if this is my outcome in speed, I could exactly know what my outcome in power would be. And so because of that, I just compared my own data versus the data that was provided by the manufacturer. And so I plotted, this is the contour map that I made of like the wind speeds observed by the turbine. And we can sort of see that the ones on the periphery, such as SK, SGK 309 and 120, observe higher wind speeds. And basically what we can say from this is that at a all done using 2023 data. And what I found was that it was through, this is the June and July data for the year 2023. And I just basically found that there was a 10% decrease in June data as compared to July data in both years, but there was somehow huge fluctuation in 2024, and I don't know what that is. And so, like basically my conclusions were that this is the ratio that that the mean and max refer by, and also from this we can get the efficiency, and basically that the 2024 and 2023 data follows the same trend but with that much larger. And I used a lot of this to send a report to help the company in sending a report to the manufacturing company on these turbines, just so that they could also predict and not be false hope with their guidance.
So, while looking at the wind patterns for the area, can you just say, is this a random process or there are geographical reasons associated with that?
Yeah. So there are all those, or the wind patterns or the.
Yeah, the curve you shown, there is a difference in that.
Yeah. So that is just how the wind is like observed in that region. Like so, the wake effect is because of all of these physical values surrounding construction, etc. But it's only for that localized region. So large scale, like wind patterns, is not what I analyzed. I analyzed what the effect of these wind patterns in this particular region is because of the construction arrangement of these turbines. So, like, are you asking how the wind patterns are?
I'm just asking, can I just consider them to be as random fluctuations and then just go off?
No, they're not random because obviously there was a trend, right? Like for if you even average over a particular day, so like if you have like a trend in a particular day and then you average that over the month, like for example, here it can be seen that largely there is a dip at this particular point and then it rises. So it's not random, like it's similar for different months, but there are some deviations. And it wouldn't have been such a like perfect curve. If it was random, it would have been more flat.
Of all the results that you have, is there something which can be actually put to any use, suggesting when you talk about so many factors, arrangement or many other factors, which can be changed to increase the efficiency?
Yeah, so so basically that would involve like doing a field visit and seeing how each of these factors affects the wake effect. So what I studied was like after there is this wake effect, how like what is the margin by which the speed, the observed speed is reduced for these turbines. So like I can basically tell them that this is the effect of the arrangement of your turbines, but I can't like basically propose a better arrangement because that way I'd have to like actually see the effect of each of these like factors on the turbines, like probably like try out various arrangements, grid like structure or more which is also studied in detail, but like as I said, this is just the
And you have this one sample.
Yeah, this is just the one sample, like this particular arrangement of turbines, and I left out the one at the right, the southeast corner because that was like
The data that you used was actual data,
from 2020.
not simulated.
No,
From
2020.
2020.
From most months, November had some a lot of times when the turbines were completely switched
So
off.
was there a reason you concentrated on the June and July data was because
just a 10% dip of June and July compared
You said
against
there's a the June data had a peculiar 10% dip.
no, that is different. So basically, June, August, sorry, not August, September and October, the mu, which is sorry, not mode ratio itself decreased by like a large amount. But here, what I'm doing is just comparing July and May and June.
So that's what I said. The 23 data and 24 data, you said there was a 10% dip in the.
Yeah.
Is 10% a significant depends upon what your each data error bar size is.
Yeah.
Can you actually compare it with your error bar?
Yeah.
When you
So,
say 10% is significant.
so my error bar was about 20%. Like
So you are within your error bar then.
yeah, that's true.
Thanks.
I just did that to see if there was like comparing across years,
But you did only for 3 years.
because there was not data.
All good. Thank you.
Anyone has any question? Okay, thank you Ananya for your presentation. Now I would like to invite Odilon Imsong, Chris Girl and Virushi Vesh from St. Stephen's College to come and present. After that we'll have a break. Okay, so good afternoon everyone. So we will be presenting on we'll be beginning with a presentation. I want you to imagine a tree in front of you, or a building. Given the position of that tree and given the velocity of the wind, can we predict or can we say anything regarding as to the aerodynamics that that tree would provide on us? Now, trees come in different sizes, but we will be narrowing it down with this specific conditions. The canopy diameter must be much greater than the diameter of the trunk, because we want to see the effect of the canopy, not the trunk. As well as the leaf area density should be greater than the set amount. So leaf area density 0.5, it simply means imagine a cube of 1 meter, 1 meter, 1 meter. Fill it with leaves and then spread it out in the shape of a cube. The area should be approximately 0.5 meters square. That's what it means. So these are the trees that fit our definitions. These are the trees that does not fit our definitions. So we will not be talking about this type of trees. This is an important term, so kindly pay attention. This is the formula that we will be using on. Out here, the u is the velocity that comes out of the tree. So imagine wind is coming out here, I'm the tree, and the velocity that comes out from behind me, that is the u. That is what we will be calculating. ut is what we call the friction velocity and is given by this formula. T tau right here is the shear stress on the building, and rho here is the air density. Z naught is the roughness length out here, Z is the height, and kappa is the bond carbon constant, approximately 0.4. So this is the formula that we will be looking at, and this will be explained by Chris, so pay attention because this is very important.
Right. So a tree specifically has two center lines. One that goes straight through the building of the tree, and the other center line is at the y-axis. That kind of divides the y-axis in two halves. This is usually in the middle of the canopy. That's because as the wind comes, the wind is divided into two parts. One, it goes up here, and one it goes down here. So center line is quite important because when this center line becomes zero, we assume that this is the 0 point. So that's when the velocity is maximum. So we plotted a graph using this formula. What exactly is this formula? Is U here, E here is the reference speed. So reference speed is essentially is when there is no tree. The wind experienced by the building when there is no tree present. U is the new wind speed, right? So there are three terms divided in this. This is the logarithmic term, Gaussian term, and the wake deficit term. Right? I will be expanding on all of those. So the wake deficit term here is essentially what is the wake? Wake is the disturbance in the flow of the liquid. The wind here is the liquid. So what a wake is, disturbance in that. So we assume we take the wake deficit here, right? So this wake deficit is actually CD d by x to the power n. D by x here is the streamwise distance, right? So this is what the wake deficit law is, right? Essentially. Then we follow the Gaussian profile. So actually this is quite interesting for us. We looked at two different data. One model was Ishikawa et al. And the other model was a study done on the MIT buildings by David H. Wood. So what we noticed was both of those graphs were forming a bell curve. We used that Gaussian profile and computed the wake here. You see the sigma naught? This is actually the wake width. And x by t is again the streamwise distance. Then at the boundary, we saw that the graph was actually not increasing linearly, it was increasing logarithmically. So this is what the logarithmic law here we use is mu tau by k log z by z naught. This is taken from the kappa epsilon reference model that already talked about. So this z is the top of the height of the tree, and z naught is taken here as 0.04 meters. Why specifically 0.04 meters? Because as you go down this height, the wind actually becomes zero, right?
So over here we see the heat maps with the velocity without the tree. So here you can see the wake, which is the wake over here behind the tree is greater, and before while hitting the tree it's very less, and with the tree over here, the velocity over here, when the tree presence of the tree, the wake which hits the building, you can see it's greater than without the tree, which means that a lot of velocity was lost due to the canopy of the tree, and it affects the wake of the whole building. Okay, so it affects the wake of the whole building, and the difference in these we can see that the velocity is affected very greatly due to the canopy of the tree. Now, with the turbulent kinetic energy, we can see without the tree, most of the turbulence is present at the edge of the building, which makes sense because the turbulence will be because of the the obstruction of the building. While over here with the tree, most of the turbulence is present throughout. It's very chaotic and it's present throughout over this region. And over here you can see it's a very large turbulence is present at this region, whereas due to the canopy it is very chaotic, but the large turbulence at the edge of the building is not present. So due to the canopy we can see it's a very chaotic representation of turbulence, whereas without the tree it's a very precise turbulence which is caused at the edge of the building. So,
Okay, so we'll be looking at some important terms here. When we use the term stream-wise land to simplify things, it's not exact definition, but to simplify things, stream-wise land, you can think of it as the distance between the tree and the building. Span-wise land is basically the width of the building, and we assume the diameter of the canopy to be 5 meters for the rest of the graph that we will be showing it to you. Oh yes, and also the wake center and the principal center is basically imaginary line that passes through the canopy of the tree, which is perpendicular to the building, which you have seen in the previous pictures. So let's just get this quick because I'll be explaining that anyways. So this is our first observation. We will be focusing on this value right here where x by d is 10. So that is the purple graph. We see that for x by d, which is equals to 10, along this area right here is where it flattens out and it asymptotically it flattens out near 1, or sorry, near 0.9. Whereas, as for the peak right here, it reaches an approximate value of 0.27. 0.27 right here. So what can we conclude from here is that the velocity ratio, it decreases asymptotically, the velocity ratio asymptotically approaches 0.9, which actually makes sense because the further you go away from the tree, the effect of the tree becomes negligible. And hence the wind speed, it dissipates. Then what we can also do is, understand from this graph is, for the same set x by d equals to 10, when we look at the minima and the maxima right here, at the principal center, which is 0 by 0 right here, at the principal center, we see that the velocity, which is the ratio out here, is the least compared to the maximum point right here, which further tells that if you're measuring the wind right at the center, then the effect of the canopy will be more as compared to the radius. One very interesting thing is that, say I'm the canopy, my diameter is 5 meters. The moment you start measuring the wind speed beyond the 5 meters, then in that case, it will be the same as the effect that I will be leading, that the effect that I will be causing span-wise will be negligible. So it is only, the boundary condition is such that according to span-wise, it's only within the diameter of the canopy. Also, as x by d ratio increases from 2 to 10, we also see that for very far trees, the decrement of velocity is more than the tree that is right in front, which makes sense because when you compare the tree nearby your building as well as far, then you will see a similar explanation for it. This is the kinetic energy of the wind between the building and the tree. Far from the center line, the turbulence is low because it starts to dissipate quickly, whereas the more closer you come to the center line, the dissipation will be much more lesser, which is again logical. So this is the summary. Wake effect becomes as the distance of the tree increases. Velocity deficit in wake region recovers due to dissipation with regards to the surroundings. At very large y by d and u by e, like u by e approaches to 1. And also the tree generates turbulence, which is dissipated as the wake travels downward. So, yeah. these are the citations.
All the ratios that you're showing about Gaussian and the logarithmic, like, are those explored in greater results, or is there any kind of special reason for it?
So, actually the thing was, we were doing a study on this and we referred to two studies. One of them was the MIT paper and the other one that I mentioned was the Chicago paper. I noticed two very similarities was there was a bell curve. Of course they took observations there, we did not have the equipment to take the readings. But what I noticed was they all were making a bell curve. Right. So I did a bit of studying on my own and I researched about the weight deficit and I figured that all of them it's not going linearly, it's going logarithmically and all of them will form a weight deficit. Why? Because essentially if you go back here, right, this is the center line. This part is what essentially is. So the wind is going downstream this way and this way. That's why the Gaussian law is being formed. It's increasing as it goes near to the Gaussian law. Sorry, the U decreases. Yeah, the U decreases as you go near the Gaussian law because the density is the maximum near the center line, so U decreases. But as you go further away at the edges, the density is less, and U kind of increases. Right? That's why you see this graph, right? It goes near to 0.9 as in towards when it goes above the y by d and it goes out. It goes far away from the center line.
And can you show the graph of velocity in the canopy, like the velocity distribution? Two to three slides.
This
Yeah.
one?
Why there is a negative growth? There is for the blue place there is negative value. What is this that they are showing?
Negative values essentially the weight is slowed very much. It's not actually zero. If I had to explain it in a way, the velocity it's kind of curving. It's not exactly this part. The dark blue part of the velocity is very slow to the point where it's kind of getting on top of the weight.
It's reversing its direction.
Yeah, it's reversing its direction because see, as I told, as it goes near the surface, the weight it has a very about area. Most of the time, we don't even feel the weight at this height. But when this data was again taken from the paper, we noticed that there was some weight, there was some erratic happening. Sometimes you see those whirlpools happening. There was something happening during that time. So it was essentially coming.
Do you actually have these raw flow diagrams?
No, not this one, but
Did you actually get any of these flow diagrams?
Those flow diagrams are not. That was actually taken from the MIT paper because this was done in a tunnel essentially, right? Those computational tunnels where they're completely covered. We wanted
You
to.
can produce flow diagrams on a computer as well.
Yes, we can. But those will be very erratic because you can't really. There's a lot of obstruction.
You can generate data because you have a formula and you can actually draw your own flow diagrams.
Yes, it's just it was my limitation, knowledge limitation. That I could not.
I'm just asking.
Yes.
Okay. So, did you actually assume some kind of symmetry for your tree, shape of the tree
Yes.
while you're handling at this point?
Yes, that was one of the very big assumptions we made. We assumed the canopy was symmetrical on each of those sides.
So
As
that means
most,
it was
because actually, if you notice, most of the trees are not that asymmetric. They are most few images here, put here. See that this is not.
no. So simpler language, you assume every tree to be spherical,
Yes.
right? And suppose just one. I just want to know one answer.
Yes.
Suppose it was not spherical, but what you have actually drawn in your figure is a rectangle,
Yes.
right?
Yes. Yes.
Can you still use that Gaussian?
Yes, in a way, because assuming let's say if this is the tree, so at this point, the Gaussian will work. But as you go outside, like this region where the density is very less, it might break. So
Yes, I didn't get my answer. Can you still use the Gaussian if you your formula, and you worked out the formula that you derived, this is derived assuming that your tree is spherical.
Yes.
I'm saying, can you,
Yes, we can.
does that,
Yeah.
where does the spherical symmetry appear in your formula?
Actually, that's we essentially when you're taking the y by d and x by d, that's when we assume that it's symmetrical. So on each of these slides, you can see that we have assumed it to be.
Which is the first term, second term, or the third term?
It's in the second term. This is the Gaussian term, right? So this is where we assume.
That your tree is
It's,
spherical.
yes.
It's spherical.
Yes. Spherical, not exactly, but symmetrical.
Symmetry.
Yes. So what I mean was, you can use it on any tree.
But I'm sure this calculation has to be done assuming some shape of the canopy.
Yeah, but that canopy not necessarily need to be spherical. It can be any. It needs to be symmetrical on
The
each side.
formula will remain same.
Yes, but it might cause some limitations depending on the density.
Did you actually derive the formula of the tree?
I actually, one of my seniors helped me with it.
Thank you all along, Chris and Vidushi.
I have one question. So can you tell us what is the Reynolds number? You are talking about fluid dynamics. And how do you differentiate between a laminar flow and a
So I
turbulent
think
flow?
I referred to you before for that. I wanted to work on the forest and everything. I figured that something came as what we call Navier-Stokes equation. We were unable to compute that.
No, my question is simple. I am just asking. You are talking about a turbulent flow, then you must be aware about that there is something called laminar flow.
Yes.
We differentiate them on the basis of something called Reynolds number.
Yes.
What is Reynolds number? Can you tell us something about it?
Actually, we are just assuming that it's a normal turbulent flow. The reason is we
You are
have
assuming
this.
what?
It's a normal turbulent flow.
Is it turbulent?
Why? Because this n constant here is actually the empirical constant depending on the turbulence. It varies from 1.1 to 1.5. Since we are in a city state, because we expect a lot of turbulence, so I took it as 1.2. Because there's not a lot of turbulence, you don't see a really high winds here.
No, but then data that you are using, I mean, the simulation that you are using is not from here, huh?
Yes, it's actually it's of North Carolina.
North Carolina is very turbulent.
No. During the summertime when it's all fine. The reason I could not find much about it in India. The model we were using was not a lot of what's not there in India. We did use Shabazz Bay at all, but that was for the question.
Thank you all along, Chris and Vidushi. Now we'll head outside for some refreshment. And the next one is Akram Verma and Dishti Ashutosh Awasthi. Please be ready with your presentation.